Damian Sercombe, University. Freiburg, yeah, from the University of Freiburg in Germany, was speaking to us about the schematic linears and subgroups of algebraic groups.
Yeah, so hello everybody, and thank you very much to the organizers. And I really I've seen how much work there is that they've done. So yeah, so the title of my talk, says what I'm talking about. It's essentially like a slightly different way than I would normally give a talk. In that, so in the last bit of work I've done, I've sort of developed a particular tool which is taking schematic unions of subgroups, and I've found that this tool has quite a few applications. So essentially, the point of this is to introduce a tool and then apply. So let's.
Oh, classic.
Yeah, right. So the what? Okay. So just some background to this. So I'm primarily focused on algebraic groups which are not necessarily smooth. Some background on this. So the structure theory of algebraic groups which are smooth, often the word smooth is implicit, is well studied. We've seen some talks already, especially for reductive groups over algebraically closed fields. As we know, they appear absolutely everywhere. So the theory of finite dimensional restricted Lie algebras. So I just mean a Lie algebra equipped with a P power map that you only see in characteristic P. It tends to go along similar lines. So, for instance, your theory begins always by fix a maximal torus. And in Lie algebras, they have an analogous notion. It tends to be more complicated. However, restricted Lie algebras can be interpreted as algebraic groups via the Demezier-Gabriel correspondence. They're a particular type of height 1, we call it, killed by the Frobenius map. And they have precisely one point as the underlying space has precisely one point, which is why they've often been ignored classically, because there's nothing there. But in a scheme theoretic sense, there's quite a bit there. So these two theories unite quite nicely as algebraic groups. So the kind of overall goal is to study this notion in a general sense, which should encompass both of these theories. And just a little bit of maybe extra motivation of why I particularly became interested in them. It was honestly because I couldn't avoid them. So I didn't want to think about these sort of things, but I took the center of something, non-smooth. I took two nice subgroups, two Borels maybe? No, maybe that's too easy. Two nice subgroups, and the intersection is not smooth. I took kernel of a nice map that's not smooth. They just kept appearing. I couldn't escape. And at some point, I'm like, I just have to learn. So, as I already mentioned, the tool that I'm talking about is I take the schematic union to be defined of a possibly infinite set of subgroups of G. And I will require that it's upward directed. More on this in a second. So we give some applications of this tool, something that I call the restricted unipotent radical, which is an analog of the unipotent radical we know well, cognate subgroups, the hypercenter. So we'll see. So the setup in this talk, K is a field, arbitrary. Characteristic P can be 0, but most of our results, not all, but most are not interested in characteristic 0. And G is an algebraic K group, by which I mean a group scheme of finite type over K. So for those of you not so familiar with schemes, I'm pretty much only interested in affine group schemes, affine algebraic groups, or in the couple of cases I'm not, it's a pretty easy modification to get from affine. I mod out by the center, deal with the affine quotient, and then go back up. So you can quite happily, if you like, think of affine algebraic groups, and one of these things, via Yoneda, they embed in GLM. But the difference between the classical way of thinking is instead of embedding them as the points, so instead of taking the k points and embedding that inside GLNK, we have to also consider all the information of all the algebras which lie on top. So we've got, so more formally, it's a functor from the category of finitely generated commutative algebras from category groups. So we got to consider the k points, we got to consider maybe some a points for a k algebra, which may have nilpotents. And so that's how you see the extra structure. You can also see it on the coordinate ring, but that's one way of seeing the extra structure. But yeah, if you are not so familiar with these things, think of them as subgroup functors of GLN. Not all subgroup functors are of this form, but you can quite happily think of it like this. All right, more formalities. When I throw the word subgroup out there, I mean a locally closed subgroup scheme, which implies closed. And we say G is smooth if it is smooth at the identity. There are several characterizations, but we want its curl dimension to equal the dimension of its Lie algebra. Or if you like, you take, let's say it's affine, you could take its coordinate ring, and you want like base change it to an algebraic closure, and then you want that thing to be reduced. That's equivalent property of being smooth. I guess reduced because we're groups. Yeah, geometrically reduced because we're groups. Yeah. Okay, so just some simple examples of the types of things I'm talking about. So the additive, we already saw this in another talk. So it's simply, I think, what we can think of it as simply a functor from A. A is a commutative finitely generated K algebra going to the additive group underlying A. Okay, and so as we know, there's equivalence of categories between affine schemes and rings. And so we have the ring, which is the polynomial ring KT here. But because we have a group structure, so how do we add the group structure onto the scheme? Well, because spec is a contravariant functor, you're putting on a co-multiplication structure to the associated ring. And what all the compatibility conditions tell you is that that thing is a Hopf algebra. And so the Hopf algebra of this guy is equivalent with this particular vector. All right, and I just give you some justification of why GA is smooth. So its Lie algebra is one-dimensional, and its curl dimension is one. Therefore, it's but let's take its Frobenius common, and by which I mean this subgroup functor. So the p roots of 0. Okay, over a field, there's going to be nothing there except 0 itself. But over an algebra with nilpotents, you'll get all the nilpotents. So there is something there. So this thing has curl dimension 0, but the same Lie algebra as G. So this thing is a non-smooth subgroup of G.
And I think it has the same Lie algebra as that.
How do I see it has the same Lie algebra? How do I see? So I tend to think of the Lie. I mean, so the Demonstrator-Gabriel correspondence would just take height 1 group schemes to the Lie algebra. So I tend to think of the Lie algebra as literally living inside as the Frobenius kernel. So it's not very satisfying, but I kind of think of this as Lie algebra. Yeah, I need to think a bit. So let me think. And afterwards, I think I'll say it.
You have to look at the points to do numbers.
Yeah, okay. Yeah, that's why I should have said.
Just thinking about the differential of it.
Yeah.
Yeah. Because the differential 0.
Yeah. Okay. Luckily, I have all the people helping me. Yeah, honestly, it's been so long since I've really thought about this. I kind of think of it just as living inside it. Yeah. Anyway, this thing is an example of an infinitesimal group scheme, meaning that for any field extension, that would be the one algebraic here, then it just has one term. Okay, so now let's go on to some of the questions which I was motivated by. So, the unipotent radical, can we remove some adjectives, in particular the word smooth? Can we get rid of that? Secondly, consider modding out G by its center. And then do it again. Does it terminate? Do we have a notion of the high percentile for those who have come across this notion in group theory, the group theoretic notion? What about Cartan subgroups? Do we have analogs of maximal tori? And finally, is there a sensible notion of a maximal subgroup? Okay, so I'm going to throw a kind of formal definition at you now. So you take a scheme and you take a set of closed subschemes. It can be huge. And in fact, we are interested in infinite size once. The category of schemes admits coproducts, so you can form the coproduct scheme. Then you take the morphism given by inclusion on each component. And you take the schematic the schematic image of this morphism. So yeah, its existence you can find in many algebraic geometry textbooks. It's the unique smallest closed subscheme of X through which this map happens. Yeah, so that's the schematic view. Now, in our case, when we're
that's a universal object.
Sorry?
Is that a universal object?
Yeah, it's a universal object. Yeah, it's in the sense of that every morphism through to a closed subscheme, yeah, it's going to go first via that. Yeah, in that sense, yeah. Okay, but really what I'm talking about is affine schemes. So in that case, it's really quite down to earth. So what is a closed subscheme of an affine scheme? It just corresponds to a quotient of the ring or an ideal. So we have a bunch of different, so this is a laser, right? It's a laser?
Yeah,
that's
okay.
Yeah, right. Nice. So we have of these guys here, each of them correspond to an ideal of the coordinate ring. So we just intersect all these ideals. The intersection of arbitrarily many ideals remains an ideal, so we get ourselves a closed subscheme. And that's precisely what this thing is here. Okay. Look at the ring, intersect all the ideals. Now, some of the behavior. So the first thing that you might think when you take this tool is it's going to be completely useless for an algebraic group theorist anyway. So firstly, let's, on the good side, what are things it does well? Well, it commutes with flat phase change. So for our purposes, you can go up to the algebraic closure of the field, no problems. Secondly, let's just try and think of, suppose you're taking the schematic union of just two of these y's. Then the union is just a push out of these inclusion maps. And this is precisely the same thing as in the set theoretic. So yeah, in that very small categorical sense, it behaves like what we want it to. But bad behavior, schematic unions need not distribute, nor vice versa, unlike the usual set theoretic notions. And secondly, the more relevant bad behavior here is when your set is infinite. Then, so let's recall, a scheme is just a set of prime ideals equipped with a Zariski topology with a sheaf floating on top of it. If you just consider the set, then the underlying set of this guy need not be the union in the set theoretic sense of the underlying sets of each of these guys. In fact, it can be very, very far away. So we have an example of where we just have affine space, the spectrum of the polynomial ring. Then we can write it as the schematic union of all these quotients. So remember what I said, schematic union was? We're taking the intersection of all these ideals. What is the intersection of all these ideals? It's just trivial. So you're going to get yourself a full affine space, but all of these guys have a unique prime ideal generated by T. And And so all of these things on the right-hand side are just going to be the exact same one-point space. So you're unioning all the one-point space, you end up with a one-point space over here. And on here, you have all of that point space. So it really is, at this point, you might be like, it's useless. Okay, why? It's useless.
Excuse me.
Yeah.
So your subgroups may not be connected.
No, not necessarily connected, no. No, they're just a closed subgroup scheme. Yeah. Okay, so let's turn our attention to algebraic groups and see what happens with this useless tool. So we take a field and we take an affine algebraic. You take a possibly monstrous set of subgroups, which are automatically closed, that's upward directed under inclusion, by which I mean if you have any two subgroups in this set, you have a third one which contains both of these two. So one nice example of an upward directed set is a chain. We take the schematic union of these guys. And so this tool I keep mentioning, I'm really referring to this theorem, which I couldn't even fit on the one page, it's so big. But the theorem says that, firstly, this thing is not just a photo subscreen, but it's a subgroup scheme of G. That is not at all obvious. You can quite easily show that the K points is a subgroup of the K points of G. That's not hard, but going to all the algebras above was quite an ordeal. So that's not at all obvious. The second part is, all right, what other properties are preserved? Normality is preserved. If these guys are all normal, then this is normal. And the third part of this tool says that let's consider one of these many, many properties of algebraic groups. Unipotence, unipotent, connected, nilpotent, blah, blah, smooth connected of multiplicative type. By the way, of multiplicative type just means if you base change to a separable closure of your field, it just means diagonalized. Living in there. Yeah. And so the third part of this technical result says that if every one of these subgroups has this property, then so does the schematic union. So there has been times when I thought that was fairly magic, just because of how badly it behaves on the topological spaces, and yet somehow you can still see all these properties. I make a remark proving, so not all of these are due to me. Smooth and connected are easy to see. So for connectedness, let's say you have the schematic union of a bunch of connected subgroups. It's going to be the smallest closed subscheme which contains them. But if you just take the connected component of that, that's going to be contained in the original schematic union. But that's the smallest, so therefore they. There's a similar thing with smooth. So smooth and connected are easy. Well, smooth and connected are easy. Of multiplicative type, to my chagrin, is that the right word? It's apparently due to Reynolds in a letter to Deline, who published it in French in 2014. The rest, I hope, are mine. So let's see if I don't get any emails at some point. But yeah, some properties for which this fails are nilpotent and solvable. So solvable, for instance, you can see in, take, say, SL2 in characteristic 2. Each of the Frobenius kernels are solvable. I think the first one is nilpotent. Anyway, each of them are solvable, but the schematic union is just all of SL2, and this thing and SL2 is also not solvable. So that's the counterexample there. And for nilpotent, you can find a counterexample inside the multiplicative group semi-direct with Z2 acting by inversion. So yeah. So now we go on to, now we've got our tool. So now we look at some applications and some proofs. So the first result is kind of a toy result, because we don't, in the sense that we don't need it for this. And essentially what I'm doing is I'm just trying to do, I'm really a group theorist, so I'm just trying to do group theory. But it's very, sometimes it's very hard. So this tool helps with that. Take an affine algebraic group, take a subgroup of this, then there exists the largest normal subgroup which contained in H, which obviously we call the core following the usual notion. What's the proof? Well, it's very simple. The normal subgroups of G contained in H form an upward directed coset under inclusion. Why? Because if you take any two of them, you just take the product, that's again normal, and of course it's again in H. Okay, and we define the core to be the schematic union of these guys. And by theorem, the technical theorem, part A and B, it's a subgroup, and by part B, it's normal. There you go. And by construction, it contains all of such subgroups. And that's when I use the word largest, I mean a subgroup which satisfies this property and contains all other subgroups which satisfy this property. Yeah, very simple. So this, you should be able to use this, you can use this to look at homogeneous spaces. And I also think, but I haven't got around to this yet, certain counting problems of, counting maximal subgroups over a finite field, these sorts of things, because you can do this in usual group theory, and I did it a bit with associative algebra, so it should have a use in counting problems. But anyway, and why it's a toy problem is because we can quite easily construct it as the kernel reaction of G on this. Okay, so a less toy application. Take an affine algebraic group. There exists the largest unipotent normal subgroup, which we call rad UG. Okay, proof goes along a sort of similar line. Firstly, you take two unipotent normal subgroups. The product of them inside G is again a normal subgroup, and it's unipotent precisely because the property of unipotency is preserved by making quotients and group extensions. Yeah, you just play around with the isomorphism theorems and you can see this. Okay, so the unipotent normal subgroups form an upward directed set. And then you take the schematic union of all these guys, and then this thing is a unipotent normal subgroup of G. That's that. Very simple proof. The original proof was very different, but once I condensed all of this stuff into this technical theorem, it's very simple. So, yeah, I thought I'd give what I think is an application maybe one day. If you mod out a G by this restricted unipotent radical, it's going to have no non-trivial unipotent normal subgroups itself. Okay, so firstly, that means you can have a sequence. You can write every group as an extension of one of these guys, which I just call pseudo P reductive, by a unipotent bit. But the main application here is that, and I think Mike mentioned this yesterday, is that when you're looking at irreducible reps of, I think, smooth connected affine algebraic groups, you can quite easily mod out through the unipotent radical, because unipotent groups have, they always fix a vector. So you can do exactly the same trick here. Now, like a caveat here, I've written down a name, which makes you think, oh, they have a nice structure. No, they're hellish. They're like, it includes pretty much all pseudo-reductive groups. It includes all simple Lie algebras, which are not obviously classified in characteristic 2, and they include all horrible extensions and infinitesimal things. So just because I gave it a name doesn't mean it has a nice structure. But yeah, it's some current work of mine to try and look at some Cartan subgroups and find sufficiently nice classes where maybe this can actually be a real thing.
What did you put it restricted?
Honestly, I think because of restricted Lie algebra. Yeah, it's not a great name, but it was the least worst name that I could think of. Yeah. No, honestly, for a long time, I was telling people, please, if you have a better name, tell me. And everybody else criticized it, but then offered nothing better, because everything's taken already, right? Reductive, strictly reductive, geometrically reductive. It's like, all right, well, I got nothing. So, The P reductive was from, because that was called the algebras, which they were called P reductive. So I also think it's a bad name, but at least I like following something that. Anyway, let's get away from my bad naming conventions. The next result looks very similar to the previous one, but this one was actually a stepping stone for the one we'll see on the next slide. So, but I guess an interesting thing here is we've taken no longer to say affine as connected. So this works for even non-affine groups, but you need connected, at least as far as I know. There exists a largest nilpotent normal subgroup. And I promise this is the last slide in which you see the word largest. There are other things going on. And the proof is again quite simple. You take the central quotient, G modding out by its center, we call this thing G1. It's a result of Rosenlicht from the 50s that the quotient is affine and its center is unipotent. So then we can just define this FG to be the pre-image of this restricted unipotent graph. Okay, it's certainly nilpotent. It's a central extension of a unipotent group, which is nilpotent. Why is it the largest such? Well, we just use a well-known theorem, which has this long name. You just take a nilpotent normal subgroup of G, you map it down by a theta, and then according to this theorem, if you have a connected affine algebraic group whose center is unipotent, then all of its nilpotent normal subgroup will be unipotent as well. So this tells us that this guy is unipotent. Normal, therefore it's contained in this. And you pull back and it's contained in this F2. Okay, so this is the ingredient for the next result. We call this the fitting subgroup in an analog of the notion for finite groups due to fitting in, I think, the 30s. Okay, so the first solid proof here that isn't just kind of a consequence of this theorem. You take a connected algebraic, not necessarily affine. There exists a nilpotent normal subgroup, which we call Z infinity G, such that the center of the quotient is trivial.
Is there anything going on with the non when you really have a non-affine?
No, there's nothing going on.
Because it just
there's nothing going on.
Split Boolean group scheme and your affine.
Yeah. When you say split, it doesn't necessarily split, right? But you have a sequence and you can mod it down to the affine. Yeah, exactly. Yeah. Okay. There's nothing.
So, all of the Abelian bright or the Boolean group scheme stuff just died in the 70s.
Yeah, I mean, the hypercenter is just itself. Yeah. So no, I can tell you almost nothing about. I'm very much focused on the affine things. Yeah. And actually, I give you another little example. I was going to say it later, but now's a good time. See how the word affine is here? This fails without the word affine. And an example is an elliptic, super singular elliptic curve. The Frobenius kernels are all unipotent. Okay, so they go up order p squared, But if you take the schematic union of all these things, well, it's not going to be unipotent. Unipotent has affine in the definition, and abelian varieties have no not finite subgroups. So it fails for that.
But can I just also put the other thing? So this is a new group, but arbitrary groups. This is a new notion. This This isn't in the middle of every other.
No,
that's massive.
No. Yeah, it's a new notion. Yeah, it's known. I mean, for Lie algebras, it's known, but it's very simple because it's essentially you have a unipotent normal subgroup, another one. You just multiply them together. You get a bigger one. So it'll terminate at some point. The smooth case is by dimension. The Lie algebra is also by dimension. But the fact that it actually terminates is not clear, and it's new. Yeah. Okay. But yeah, you correctly pointed out that I tell you nothing about abelian varieties to my name. Anyway. Yep. Okay. So and you'll see. Oh, sorry. Not next thing. So yeah, the first couple of slides mimic the proof of, or the construction of, in usual group theory quite closely. So we have to look at ordinals, and it may be intrinsic, or it may be because I'm not clever enough to figure out how to not look at ordinals. More on that later. So for every ordinal, what are the ordinals? Let's refresh our memory. It's 0, 1, 2, supremum of all these guys, which is called omega. Then omega plus 1, omega plus 2, omega 2, omega squared, and then a whole world which I don't care about. Yeah. So I want to define a normal subgroup for every ordinal in an inductive way as follows. The zeroth thing, which I'm calling the zeroth or the alpha center. The zeroth center is the trivial group. The alpha plus 1 center, you take G, you mod out by this guy, you take the center, and then you pull it up under the projection map, and you get the alpha plus 1 center. Okay, for example, you take the center, ZG. How do we get the second center? Well, you just take G mod ZG, and then you take the composition of both these maps, and you kernel of this composition. Okay, but you run into an issue here, because not all ordinals can be written as 1 plus another ordinal. So this first infinite ordinal, omega, the supremum of the natural numbers, isn't 1 plus anything. So these things are called limit ordinals. So what do we do with limit ordinals? Then we have to make this definition. This is the schematic union of all the smaller ordinals. Okay, so why does this definition make sense? We need these things to be normal. Well, this condition is not difficult because you're pulling back a normal subgroup under a quotient map, so it's again normal. But for this one, it's not immediately clear that's subgroup scheme, nor that it's normal. Luckily, we have that technical theorem which tells us that precisely it is. So we apply theorem 1, A, and so yeah, this is a difference between the usual group theoretic construction, in which this is quite easy, its existence, but you need this big technical theorem to even show that this makes sense. Okay. So what we have is a upper central series of G. We have Z0, Z1, Z2, we do it all through the ordinals. Now, the nice thing to note is that it's going to terminate. Why? Because G has a cardinality. And you can think of this as living on the line of ordinals. So it's going to stop before it hits that cardinality, because the cardinality of some is bounded above phi that of G. So this is going to terminate at some point, some order.
What do you mean by cardinal? The parents?
No, cardinality, is that there? Oh, yeah, like alpha, something. Yeah, so there exists a least ordinal such that this thing terminates. And so we define the hypercenter to be this guy, the terminating. By construction, the quotient G modded out by the Z infinity has trivial center. Definitely by construction. Z infinity equals Z infinity plus 1, therefore the center of the quotient is trivial. So what have we done so far? The proof is pretty much identical to the usual group theory construction with the added machinery of the schematic unions. But what does the theorem say? The theorem says there exists a nilpotent normal subgroup center nilpotent. That's the key word here. So we've done everything except nilpotent. So, and again, as you mentioned before, am I saying anything about non-affine case? The answer is really no. We simply project down and use this theorem of Rosenlich's. So it suffices to assume G is affine, its center is unipotent. And in this case, the claim is that the hypercenter is unipotent. And we just do this by induction on dimension. So the first thing to think of is if the upper central series terminates up finitely many times, then we're done. This thing is indeed nilpotent. I mean, it'll be an upper central series of the hypercenter. Maybe not. It'll be a central series of the hypercenter. Okay, so assume otherwise. This implies that the dimension of, so remember this is the schematic union of all the Z0, Z1, etc. This implies the dimensions. We're in a Noetherian scheme here. If we get greater and greater finite things, we're going to get something in positive dimension. So that deals with the dim equals 0. Okay, so now we consider the first infinite order and the natural projection to this map here. Now I'm putting this statement as I'm throwing it up there, but there's quite a lot of work involved, but maybe not so illuminative. So we check that both of these guys are unipotent using some classical results of, you get as a Gabriel, that sort of thing. And also it uses some classic results of Gabriel, and also the theorem 1, the technical theorem, and corollary 5, which is the existence of this fitting subgroup. Yeah, and the idea from memory is that you could show that you had a chain of trigonalizable nilpotent subgroups. And then the trick was showing that the nilpotency class was bounded, and then using theorem 1c, which says that if you have a schematic union of nilpotent subgroups with bounded nilpotency class, then it terminates. So that is something like that. Okay. Now you can, if you mod out by a subgroup of G, or the subgroup of the hypercenter of G, a normal subgroup, then your upper central series of G just goes nicely downstairs onto the upper central series here. So this condition pops out. And so what have we shown? We've shown that Z infinity G is an extension of Z infinity G omega, which, so we have shown that G omega is this mod this. This has positive dimension. So the dimension of this is strictly less than that of G. Now, in this hand wave thing, I've told you that it's centric in unipotent. Therefore, applying the inductive hypothesis tells us that it's hypercentric. Okay, so the inductive hypothesis tells us that this is unipotent. Now, by my hand wave thing, after this is unipotent, which is the kernel of this map. So we have an extension of unipotent groups, which I already mentioned is itself unipotent. So this thing is unipotent without. Okay, on to the next application. Checking how I'm doing time. So Cartan subgroups. So Cartan subgroups and maximal tori are quite well studied for smooth algebraic groups. So maximal tori are incredibly well behaved. There's pretty much only one conscious class, as long as your base change was separate from closure. Maximal tori and the Cartan subgroups, and they're used to rigidify. In the theory of restricted Lie algebras, there's an analog to this notion that behaves a bit worse. So with smooth groups, there's pretty much one maximal, one class. With Lie algebras, there can be multiple classes. So we've introduced two definitions that in fact reduce to the usual definitions of the smooth and of the height 1 case. Height 1 and restricted Lie algebras are just the same thing. And so the definitions are as follows. And okay, the fact that they do indeed coincide with the usual definitions is not obvious, but it is true. A Cartan subgroup is an affine algebraic group, or even just take the word affine away. It's nilpotent, and it equals the connected component of its normalizer. So this looks exactly like the Lie algebra definition, but the smooth definition is usually the centralizer of a maximal torus. And I had some anonymous reviewers telling me they didn't like this definition, but I stick by it. This is what it should be. And let's just give it a name, because the phrase connected multiplicative type subgroup, which is maximal amongst all connected multiplicative type subgroups of G, doesn't roll off the tongue very well. So when we say something is a connected multiplet type group, we just call it a toroid. And if it's maximal among such things, it's a maximal toroid. And the definition of a torus is a smooth connected multiplet type group. So all I've done is taken the word smooth and taken away. The theorem, the main theorem, says that if you have an affine algebraic group, then we have a one-to-one correspondence between the set of maximal toroids of G and the set of half-ham subgroups of G. And this is quite nice because there are other properties which I won't go into that it has been the case that they work over smooth groups, they work for restricted Lie algebras, but they fail very badly, or in general. And often the point they fail is going from height 1 to height 2. Something very weird happens there. So the fact that this holds is actually surprisingly nice. Moreover, G admits at least one type of right? It's not immediately clear, but with the schematic union tool, it is. Because the properties of, say, multiplicative tightness and connectedness are preserved by schematic unions. So if you take a chain of these, the schematic union is going to be one of those things. So that does exist. Yeah, so you do need this theorem, and that's not why. And let me just, I think I have a little bit of time. So let me just give you an example. I think I mentioned this at the other day. So the example I gave, I think, was let G equals alpha P. So remember, we saw this thing before. It's the peak throughs of unity. Semi-direct product with the multiplicative. So this is a non-smooth algebraic group. It has this alpha P there. It has precisely one maximal torus. This G here. And in fact, it has the extremely weird property that this thing is, so it's unique. This is the reduction of G, in fact, but it's not normal. And by normality, we have to think of all the algebras upstairs. There's some weird stuff that goes on with algebraic groups. So let's think of, so when you're looking at this as a smooth group there, it's like, oh, it has one maximal torus. Okay? But what about maximal toroids? Well, in fact, the Frobenius kernel of this is alpha P with mu P. And so you get, this is just the Frobenius kernel of this. And so you get a whole bunch of complements of alpha P that are maximal amongst the maximal toroids. There's only one of these mu P which is not maximal, and that's precisely the one that's found in here. So in this example, you get kind of two classes of the things. You get this guy, it's not even a class, it's literally just one thing. And then you get kind of a class of these mu P's floating around the alpha P, except there's one that's in here. Okay, next and final sort of part of the talk is the maximal subgroups. What is a maximal subgroup? So the first thing I observe is that, take an affine algebraic group. If the dimension is positive and G is connected, there's no such thing. Why? Because you take any proper subgroup, and then you take a sufficiently large Frobenius kernel, and you take the product here, nothing's going to be bigger. And the reason is because the Frobenius kernels are schematically dense in G, right? So the schematic union of all of them will equal G itself. There's no such thing as a maximal subgroup. So what are all those people talking about? What are like Liebeck and Seitz and everybody talking about? Is it nonsense? The answer is yes. They've been talking nonsense all this year. No. No. Corollary. You take an affine algebraic group. You take one of the properties listed in this theorem. Then you take a subgroup which has this property. Then it is contained in a maximal such subgroup. So you need to talk about a certain property. And the proof is very simple with this technical result. you take the post set of subgroups which contain this P, and which I probably should use a different letter, but the property P under including, and then you take a chain as post set. Okay, so a chain of subgroups will satisfy this property. According to theorem, the part A and C, it's a subgroup and it has the same property. So it's an upper bound. It doesn't just stick in one somewhere. It has a maximum element. Okay, so let's flick back for a second. Remark, yeah, it fails for non-affine G, by which I mean unipotent statement fails and multiplicative type fails. And the unipotent counterexample was the supersingular elliptic curve, which I mentioned. The multiplicative type is an ordinary elliptic curve, would be a counterexample. But the rest of the theorem, I think, still holds. Okay, so let's go back and just have a look at that list of properties for a second. Where is it? Here. Okay, so the real answer to the question is, what has all those people been doing all these years? Well, they've been looking at these two properties, smooth and connected. So they've been classifying maximal smooth subgroups. They've also been classifying maximal smooth connected. But we have a whole zoo of properties which may be interesting, and in fact, in some cases, are quite interesting. So just to conclude this talk, I want to zoom in on, I guess the bottom one and the top one. So the bottom one, if your G is smooth, so that's unipotent multiplicative type. Yeah, so if you take a smooth group, then every maximal multiplicative type subgroup is smooth. If you add the word connected, you get these things I mentioned called maximal toroids. So what that means is that if G is smooth, every maximal toroid is indeed a maximal toroid. Okay, and this is a consequence of the rigidity of multiple types. The analogous statement for unipotent subgroups fails. And one counterexample is PJL2 in characteristic 2. So usually when you're looking at a reductive group and you want a maximal unipotent subgroup, you take the unipotent radical of Borel. But in PJL2 in characteristic 2, you get a little bit extra. You get the Frobenius kernel of the other group. So in fact, maximal unipotent subgroups of PJL2 in characteristic 2 are of this form. Alpha P, it's a semi-direct with a GA. Yeah. Let's get a little bit more. Okay, but so I have to give a little bit of an extra condition here. And my extra condition, and so the question is, this gets a little bit extra, but essentially this is because there's a normal unipotent fit in this example. It's an alpha 2 times alpha 2. So the question is, all right, what if you get rid of the normal things? Does the problem still happen? And so that is reflected in this condition here. And in practice, all it means is just, so let's just be really simple. Let's take a simple algebraic group over an algebraic closed bit. Let's throw in the bin SO2n plus 1 in characteristic 2, because they have this like little normal on it. And think of all the other ones. And the question is, does there exist a maximal unipotent subgroup of G which is not smooth? And if so, classify them all. Yeah, I'll talk with Ben a little bit about this, and yeah, I'm pretty sure there is. But how weird they get is, and also another thing I know is that for a fixed G, if you let P be large enough, it doesn't even have to be that large, then the answer will be no. I think you can even reduce it to characteristics. I think you can do that. And I also think there will be examples, but not many. So yeah. And let me just check the time. So that's what I was planning to end with, but I've got like 2 minutes. So I'm going to say one of the 10 minutes question, right? Yeah. And so the other thing is, so stepping back for a second, remember that we constructed this upper central series, and it terminated somewhere along the ordinals. It's actually an artifact of the proof that for any G, the length of the upper central series of G is connected, is strictly less than omega squared. And this is precisely, it falls out of the proof, because every time we mod out by a z omega, our dimension is going down by 1. And algebraic groups have finite dimension, so you can only do that dim G times. But my question is so does the upper central series of every connected G terminate after finitely many terms? I don't know. Driving me crazy, but I don't know. So one thing I do know is that if you relax the word connected, so my theorem said that if G is connected, there exists a nilpotent normal subgroup. That fails if G is disconnected, but the word nilpotent fails. But you can still define the hyperset, which is fine. And if you allow a disconnected example, I know a disconnected G such that length, let's just call this lambda equals omega plus 1. Yeah, so that's all I know. So I guess that's kind of 2 open questions. Yep, so leave it there. The question? Yeah.
So this non-smooth, you can have this over algebraically closed field also, right? So we know that for this smooth group, the over algebraically closed field, all maximal torics are conjugate.
Yeah.
Will that work in maximal? What you define maximal toroid?
No, I mean this example. I mean they have different dimensions. So here, yeah, it's actually that question, if framed quite precisely, is a very good question. The answer will always be no. So in a restricted Lie algebra, so that's a very simple example. You can have maximal tori, they call them, which is just my notion, of different dimension. Right. And then there's questions of, so often like in work of Premat and things, they often use the word fix a torus T of maximal dimension. But even they are not conjugate. That actually was only proved, that was a conjecture of Premat, and it was only proved like a couple of years ago or something. And then there's this notion of generic tori, things like that. So the answer is no, so strongly a no, and it probably gets even worse up here. So the question of which one do you want to rigidify G? Because if you pick a different one, you get a different root system. So that's already a known, very complicated problem in restricted Lie algebras, and it only gets worse upstairs. But some stuff is known about it, like these generic tori, and it's an ongoing area of research. So yeah, the answer is unfortunately no. And in this example, it's quite clear. This example, so this one has dimension 1, and the rest of them have dimension 0. But in here, there kind of is 2 classes. I guess you want to take the automorphism functor of this and say, is there an automorphism between these things? So you don't want conjugacy by a point, because that will tell you absolutely nothing for infinitesimal groups. You want but yeah.
So you're saying that two maximal tori can have different times.
Right? Toroids, yes. One of them is this one. One of them is this one. And when you flip down to Lie algebras, which they're all finite in a group sense, but in a Lie algebra sense, they have different dimensions. So even in the very specific Lie algebra case, they can have different dimensions. Yeah. Yeah. Any other questions? Yeah.
From TGL, for example, in the GA, is there a different product?
No. I don't think so, no. I think it has this form. I wrote it down somewhere. Yeah, give me a second. I can find it. If anyone wants to ask another question. Yeah. I've written it down somewhere.
Yeah. And for the GA can still be great for that out.
Yeah.
What the action?
Left multiplication. Yeah, left multiplication. For this one. So it's just the action coming from the action of Gn on GA by left multiplication. Oh. So alpha is just the previous kernel of GA. Yeah.
So you're starting with algebraic groups, meaning you find that type over the field.
Yep.
There are various other classes of groups over fields that people work with. So
In groups and things. Yeah.
Trying to finalize induction is the thing you do within.
Is it?
That makes sense. Does this?
No idea. But yeah, he's already hacked me with a couple of these questions. Does this sort of thing work for students?
I think it does.
I would take a very weak guess that it does, but I'm not really knowledgeable enough to answer that. Yeah.
I think this is in order for the union to be a subgroup, really this stuff is
Yeah, oh definitely. Yeah. I mean
is that
yeah, you really need you also need exactly that condition just in groups, just in abstract groups, right? If you take two subgroups of a group, they union is so group. Yeah. That's why we speak about subgroup generated by groups. So yeah. Yeah.
Am I correct that the Frobenius kernel is often solved?
No, it's nilpotent. The Frobenius kernel of SL2, the first one, is in characteristic is nilpotent. The second one was solvable but not nilpotent, etc. But they're all so nilpotent, solvable but not nilpotent, etc. Schematically known as philosopher. Yeah, but I mean SL2 is not talking. Is what I'm saying. Yeah.